Hello, let's talk about Taylor series. The idea behind Taylor series is given a certain function, we would like to write that function in terms of a power series that converges to the function. We call these power series Taylor series. Before we get into the details, let's talk a little bit about something called factorials. If we take a positive integer n and write an exclamation mark, this is called n factorial. N factorial is 1 times 2 times 3 times 4 times 5, etc., until we get to the positive integer n. So, for example, 4 factorial is 1 times 2 times 3 times 4. 2 times 3 is 6, 6 times 4 is 24. 3 factorial is 1 times 2 times 3, or 6. 2 factorial is 1 times 2, 2. 1 factorial is just 1, and 0 factorial, well, by convention, 0 factorial is also 1. Now that we have an idea of what factorials are, let's talk more about Taylor series. Here's the idea behind Taylor series. If we have some function f of x near an x value of a, we wish to build up a power series, and we want to build it up so that the first and the second and the third and the fourth, so that all of the derivatives of the power series match the derivatives of the function near x equals a. For example, let's take the function f of x equals e to the 2x, and let's think of this function near an x value of 0. Turns out that this power series p of x represents this function if we're close to an x value of 0. Let's not worry about where this power series came from for the moment, but let's take a look at the derivatives of the function and compare them to the derivatives of the power series. And what we want to notice is that the derivatives of the function at x equals 0 match the derivatives of the power series at x equals 0. Let's take a look. For the function, if we take the first derivative, it's chain rule. We get 2 times e to the 2x. The second derivative, we take a derivative again, and we have 4 times e to the 2x. We could take another derivative, and we have 8 times e to the 2x. That's the first 3 derivatives of the function. Now let's look at the derivatives of the power series. When we take derivatives of this power series, the 1 goes away, and we have 2 over 1 factorial times 1, that's just 2, plus 4, the derivative of x squared is 2x, so we have 4 times 2x divided by 2 factorial, plus the derivative of x cubed is 3x squared, so we have 8 times 3x squared divided by 3 factorial, etc., etc. Let's take a second derivative. The derivative of 2 is 0. And when we take a derivative of this linear term, we get 4 times 2 over 2 factorial. That is simply 4. And the derivative of this third term is 8 times 3 times 2x divided by 3 factorial. If we take a third derivative, the derivative of 4 is 0, and when we take the derivative of this linear term, we have 8 times 3 times 2 divided by 3 factorial. 3 factorial is 3 times 2 times 1, so all of those factors cancel, and we're left with 8. Now, we're interested in these derivatives at an x value of 0, so let's compare those. For the original function, f prime of 0, we plug in 0 to the first derivative. We have 2 times e to the 0, that's 2 times 1, that is 2. The second derivative at 0 is 4 times e to the 0, that's 4. The third derivative at x equals 0 is 8. Compare that to the derivatives of the power series at 0. When we plug in x equals 0, everything goes away except for the constant terms. So the first derivative of the power series at 0 is a constant of 2. The second derivative is 4. The third derivative is 8. Notice that the derivatives of the function and the derivatives of the power series match. So, in other words, if we compare our function and this power series, they have the same derivatives near an x value of 0. Now, we can notice a pattern here in this power series. We have 1, 2, 4, 8. Those are powers of 2. And in the denominator, we have 1 factorial, 2 factorial, 3 factorial, etc. We could write this power series in summation notation. We could express this power series as the sum, where n goes from 0 to infinity. And then we have 1, which is 2 to the 0, 2 to the first, 2 squared, 2 cubed. So we have powers of 2. And then we have powers of x, x to the n. And then we're dividing each term by n factorial. This power series expressed in sigma notation is the shorthand form for the power series that we started with. Let's take a look at this comparison in Desmos. Here we have the original function in red, and we have the power series given in blue. If we increase this value for m, that will give us more and more terms of the power series. And notice that as we increase more terms of the power series, the graph begins to look more and more like the graph of e to the 2x. In fact, if we were to let the number of terms go to infinity, our power series would exactly equal the function e to the 2x. Once again, the important idea is that the derivatives of the power series match the derivatives of the function at x equals 0. This gives us the definition of Taylor series. If we have a function f of x centered at x equals 0, the Taylor series is this expression here. We have the same x to the n over n factorial sorts of terms, and then we have these coefficients, which are the nth derivatives of the function at 0. When we're centering at x equals 0, the Taylor series has a special name. This is called not just a Taylor series, but a Maclaurin series. In general, if we center around a different value other than a, we have a general Taylor series. Here's the definition for a general Taylor series. When we center around x equals a, we take the nth derivative of the function evaluated at a, and we have x minus a to the n divided by n factorial. Using this formula, we can find power series that represent a given function f of x.